Um, One of the things that gets tricky with reaction rates is that there will be times that it's really convenient to monitor your reaction in terms of one reactant or one product, and it's so much easier to monitor that one over any others. If you're doing solution phase work, and one of the reactants or products is strongly colored, like Allura Red in the Beers Law lab from 1142, or Crystal Violet from the Integrated Rate Law experiment in 1142, spectrophotometry in Beers Law absolutely is the way to go for monitoring that reaction. Other times you might have gas phase chemicals, and you may have a sensor that's sensitive to one particular chemical, like an ammonia sensor. And in that case, you want to make sure that ammonia is the chemical you're monitoring. But what is the connection between the reaction or the rate of appearance or rate of disappearance of that one chemical and the overall reaction rate, or the rate of the appearance of disappearance of that chemical compared to other chemicals? There will be reasons that you need to know those relative rates. Well, those relative rates are expressed by the coefficients. The coefficients in a balanced equation tell us the molar ratios. That's why we use them for stoichiometry. We can also use them for reaction rates because the reaction rates are given as molarity per time. And so molarity is moles per liter per time. And so having those moles up there make it useful to use the coefficients to relate one chemical to another. Okay, so let's relate these rates. Let's say we have a reaction like this one where every chemical has a different coefficient on it. Just to make this a little bit more concrete, to indicate what I mean by different chemicals having different rates, think about a hypothetical situation where you are putting the finishing touches on building a car. And the last thing that has to be done is you're going to put 2 windshield wipers on the front windshield, and then you're going to get 1 car. So our mole ratios here are 2 windshield wipers to 1 car. So if I look at how fast my windshield wipers are disappearing, and let's say you're very slow and very tedious and it takes you a whole hour to do this. So my rate of disappearance of windshield wipers is 2 windshield wipers per hour, but my rate of appearance of completed cars is 1 car per hour. We need to keep those mole ratios in mind. And of course, because of how we defined the reaction rate, we need to divide out all of those coefficients. So in this particular reaction that's given on this slide, where we have we have 3 hydrogens reacting with 1 nitrogen to give us 2 ammonias. We apparently, for this reaction, have a sensor that tells us all about ammonia. And so we need to take this ammonia rate, and from the ammonia rate, figure out the defined reaction rate, as well as the disappearance of nitrogen and the disappearance of hydrogen. To give myself a little more room, we're going to do this on the next slide. All right, there's room to write over here. So let's take a look. First question is, what is the reaction rate? Now remember, the formal definition of the reaction rate needs to give us a unique number, no matter which chemical we're monitoring. So when we define the rate, we divide through by the coefficients. So for ammonia, it's a product, so we leave a positive number. We're going to divide by the coefficient of 2, and then we'll do the change of ammonia over, there's a delta there, over the change in time. So it'll be 1/2 of 1.15 moles per liter per hour. And so if I run that through my calculator, I'm going to take 1.15 divided by 2, because dividing by 2 is the same thing as multiplying by a half. And I have 0.575 moles per liter per hour. For the second part, we're looking for the rate of disappearance of nitrogen. Now remember, all this stuff about appearance and disappearance is just a way of making sure the numbers are always positive. So here we go. We're going to set this up as dimensional analysis. So let's start with what we were originally given. We have 1.15 moles. And now here's the trick to make this all work out really easily. Let's write moles of what? That was moles of ammonia divided by liters and divided by hours. So to convert from ammonia to nitrogen, we're going to use the coefficients from the balanced equation. Ammonia has a 2 and nitrogen doesn't have anything written, which means it's a 1. So for every 2 moles of ammonia, we get 1 mole of nitrogen. And so moles of ammonia cancel, and if you run that through your calculator, you're going to find 0.575 moles per liter per hour for nitrogen. One more example here. Let's relate this to hydrogen. So if we start with the 1.15 moles of ammonia per liter per hour, and then go with 2 moles of ammonia, that's the coefficient from the balanced equation, and ammonia is down in the bottom to cancel out what we were given. But now we're looking for hydrogen. The coefficient on hydrogen in the balanced equation is a 3. So 3 moles of hydrogen. Now moles of ammonia cancel with moles of ammonia. And so now we've got 1.15 times 3 divided by 2. And that's going to be 1.73 moles per liter per hour of hydrogen. Alrighty, there we go. Next slide. Okay, it's not letting me advance to the next slide. Let's try this. Okay, let me stop it and we'll see what happens. Sorry about that glitch at the end of the last slide. My edition and my version of PowerPoint updated, and so this is the first time I've used this particular interface for recording, and apparently I don't have all the buttons figured out yet. Okay, so last slide, this clicker question. If oxygen is consumed at a rate of 0.5 molar per minute, what is the rate of appearance of carbon dioxide? Okay, I strongly recommend you pause this video for a moment and see if you can figure this out on your own. Okay, now let's start up again, and let's start with what we're given. We're given the half molar per minute for oxygen. And just remember, molarity has moles, right? Molarity is going to be moles per liter. So we'll write moles per liter per minute. And what we were given was information about oxygen. So that's moles of oxygen per liter per minute. And if we look at our conversions, we need to relate moles of oxygen down in the bottom to cancel out to moles of carbon dioxide, since that's what we're looking for. The connection is the coefficients, 7 oxygens for 4 CO2s. So I'm going to put a 7 down in the bottom with oxygen and a 4 up in the top with CO2. And what's that going to give me? 0.5 times 4 divided by 7. And that will be 0.286 moles of CO2 per liter per minute. Moles of O2 go away. So that looks like it's going to be answer B. All right, that wraps it up for this section. Good luck.